Okay, it says you're live right now, so let me just hear something. Tell me if you can hear. Tell me if you can hear me good. Also, yeah. So also, I could maybe. Oh, I think it's gonna be fine. I think it's gonna be fine. I'll wait and set up a little bit. Set up everything before 3 a.m. So. Oh, hello, Blagoy. Hello. Yeah, let's go. Let's go and first just find the problems. So here says IOI day 1 and day 2 problems. We'll probably read. Nice, nice. I don't know what is the delay actually, but I will try to answer to every question. Uh, all problems can have been added. You may access them here. So here are the 6 problems. Let me just, so here, how I'm supposed to log in? Oh, come on, let me try on the second monitor logging in with like Google authentication or something. Okay, I think that worked. Yeah. So there are 6 problems. We'll maybe read all of them or something. I'm not sure. Maybe the first 3 problems, but they have been tried here. But I don't know what is this points. It should be like 100 points per problem, but maybe they have some other system in DMOJ. So I'm not sure. But I don't know. It's 4 minutes until this. But should we start or should we maybe wait 2 more minutes? Other thing, yeah. So let's go into the IOI 2022 scoreboard just so we can see here. We must mention that Blago here in the chat has competed here. So let me just. So of course we're from Macedonia, and Damian has won a bronze medal, I think. So yeah, here he is. He has 60 points on problem 2, which kind of says that maybe problem 2 we should take a look, but we still don't know. And problem 2 and problem 3 in the second day also some points. Marco Petrov is also has some points on problem 2. And both days, Blago here has points on problem 1, which means that it might be actually more interesting to take a look at problem 1, but we'll see. And Ivan has points on problem 2 in the second day. Some more points. So we'll see how it goes. I was surprised that the first 4 places are not the Chinese team. Only the first 2 places are the Chinese. So kind of interesting thing to happen. Most of the time, I would think that the first 4 places were, since they are legendary grandmasters, and yeah. I don't know this Antoni guy, so let me just see here. He's probably some LGM as well, so. Yeah, IGM. So I mean, not surprisingly, and Tanaka. Yuki Tanaka um, is what? Cold Forces or Ed Coder? No, this is not him. Maybe Ed Coder. The second problem kind of screwed me. We'll see. We'll see. We'll read the problems. I'm just waiting for three o'clock. IOI fun fact. Okay, whatever. Let's start reading them because I haven't read them, so and I really wanna read them. Okay, so we'll start from the first three problems. Let me see the second one. Just taking a look. Okay, there's some graph theory here involved, so that should be interesting. And of course, some typical IOI problem. Okay, okay, okay. Let's go. Let's go. Closing time. Hungary is a country with 10 cities, numbered from 0 to n-1. This I like. The cities are connected by n-1 bidirectional roads. Okay, so there is a tree that has weight. That allows one to travel between the cities with j units of time. Each road connects two different cities, and each pair of cities is connected by at most one road. A path between two cities is, of course, a sequence. Yeah, it is possible to travel from any city to any other, so it's one component. The length of a path is the sum of lengths of all paths. Okay, this is quite good defined. In Hungary, many people travel to attend the Foundation Day festivities in two major cities. Once the celebrations are over, they return to their homes. The government wants to prevent the crowd from disturbing the locals, so they plan to lock down all cities at certain times. Each city will be assigned a non-negative closing time by the government. The government has decided that the sum of all closing times must not be more than k. More precisely, for each I for every city, the closing time assigned to city I is a non-negative integer ci, and the sum of all must not be greater than k. But why the sum of all? Why not the okay? So the sum of all. That's kind of weird, but consider a city A and some assignments of closing time. We say that the city B is reachable from city A if and only if either they're equal or the path between these cities in particular P0 to P. Yeah, satisfy the following condition. The length of the path is at most C. The length of a path, so traveling from this city to this city is at most C. Yeah, so you want okay, so I understand this. I understand that this city is closed. You cannot travel through there. This year, the two main festival sites are located in city X and Y. For each assignment of closing times, the convenience score is defined as the sum of the following two numbers: the number of cities reachable from city X and the number of cities reachable from city Y. Note that if a city is reachable from X and Y, it counts twice towards the convenience score. So this makes the task kind of simpler. Your task is to compute the maximum convenience score that can be achieved by some assignment of closing times. Oh, I see. So K is given, of course. Okay, very interesting. Very interesting. And what are the subtasks, of course? So you have for 8 points the length of the city from city X. So let me see. So there's this, then how much time? Uh, questions. So I mean, this question that was posted in the comments: how much time should I give daily? I, you shouldn't ask me that kind of question, since like it's more important to give consistency than like you give like 6 or 7 hours per day. You will be burned out really quickly. So like just spend 1 or 2 hours per day, but spend it each day, and like try to solve as harder problems, or try to learn something. But don't just burn yourself out. So yeah, just consistency is more important than the amount of time. But okay, however, I want just to first, and then we'll answer some more questions if you have. But first, so the length of these cities is greater than 2K. It means that, okay, what does that mean? It means that they don't, they don't intersect the, yeah, so the reachability don't intersect, can't intersect for 8 points. For this, the road network is linear. So you can get a lot of points by just assuming that the road network is linear. So the road network is linear means that there is just like a path. It's a path, and then CDX and CDY. So a lot of points can be gained by just looking at like this. And then more points can be gained for, now Sn is what, a sub, what is Sn here? Where Sn is the sum of n over all calls. Yeah, so okay, so I understand this. Okay, this makes perfect sense. Now, okay, how do we approach this? Let me just take my trusty tablet. Kind of interesting problem. So there are a couple of things that we need to go through here. We need to go. So essentially, the times that we are. So what are given? Describing the road connections, describing the road length, the upper bound on the sum of closing times. So the sum of closing times, because we want to minimize the sum of closing times, and yet we want to make them more reachable, we kind of want to maybe wait, maximum convenience score is computed as the sum of these two things. So we kind of first, I'm kind of considering, is this a monotonic function, right? Because this sum is, can we prove that this sum is monotonic given k? Given k, if this is optimal, can we go and say that this is monotonic? Of course, if k is bigger, then the convenience score is bigger, so that should be monotonic. Yeah, so that's monotonic since this is just a sum and not there's no inclusion exclusion. This is monotonic as well, right? So of course, Okay. So this is easily proven. Now, should we take a look at while the road network is linear? Or we should just maybe kind of skip that? I mean, if I would be on Olympia, definitely the first thing is to solve where the road network is linear. That's a subtask. So, but I think solving this, I just want to think about how this can be done on a tree. So there is some priority here in a sense of the way that you need to give, let we can root the tree in X, and then there is this, so we can take a look at X and Y as like separate roots of the same tree. But then if I take a look at X, then the closing time, so this kind of reminds me of this problem on call forces that this DP problem, but this is not kind of a DP, but like it's just like a DFS problem, I would suppose. So if I root the tree in X, and if I close something here, let's say I close something here at some specific time, then everything of this is kind of gone. It's unaccessible. So I want to not close, I want to cleverly close this. So the sum now of the closing times should be smaller or equal to k, right? That's the constraint, right? The government has decided the sum of all closing times must not be more than k. Yeah. So there's this weight here. Mm-hmm. Interesting. If I plot this in a way that makes sense, so first I will take a look at this as a way of like, so let's say that this is time, right? Then if I plot this, it says that after 10, let's not make these values really big, but like let's say it's like something like this, okay? I'm just randomly assigning values here. So it says that after 30 things, I can close down this and still get it. So okay, after 10. So let's say 10, 20, 30, 40, 50, 60, 80 or something like that. And it says after 30 things that I can kind of I can walk up to here and then I can close this. I will get only one. Then after 10 things, I will do this. Then after here, I will after 40 things. But now this should we draw it like this? But now the sum here when I add up, it's now no longer equivalent. It's now different. So only sometimes there will be some event that changes the graph into this, like still like monotonically, but it only some certain times will change the graph. Hello. Okay, so interesting. After the sum of closing times, the closing times of very further things here will be 0, right? If I don't want to reach them and to some point, then there will be 0. And since the graph, the closing time can be 0, right? For every assigned is a non-negative integer, ci. Yeah. So the closing time can be 0. Cool. So we assign to some of them the closing time of 0, and to some of them we assign the closing time of the minimum of the shortest path to x. Either we assign that to the shortest path to x, because that's the time that it will take to come to there. Do we need +1 or something? Is at most c. Yeah, we don't need +1. So it's either 0, it's either the shortest time to come to there, the shortest path through x. And now when we have x and y, now the problem becomes into a way that, okay, so we have x and y, there's some this is the LCA of x and y, and then there's something here. So first we need to first say that, okay, my conjecture, it's not a lemma because I just can't. I mean, I maybe can prove it mathematically, but my conjecture is this: CI is either the short, it's either 0 or now here it's like not the maximum, but it's either 0, the distance between I and x, or the distance between I and y. I think that's my first observation. Yeah, exactly, block. Exactly. Distance from y to it, or the maximum of the distance from x or y. Yeah. So now the maximum of the distance from x to y, it's actually either this or this. It's like this is the maximum, but this is my first conjecture. Okay, so that's some progress. Now, okay. So how do I decide whether I want this or this? That's the problem. That's one problem. How do I decide it? So we know that this is possible. We know that this k is limited to k, right? Then we can because it's monotonic, we can like possibly binary search to what point. No, not binary search. It's not quite binary search. It's interesting. Uh, First we want, yeah. It's not binary. It's like just like a priority queue, actually, isn't it? Can you prove that this doesn't work? Like, can you just can you just take always like the minimum here and open that up? But no, actually, yeah, because this is the sum. Hmm. Like I'm thinking of like some priority queue. Some of the ideas from the competitors tried was alien trick and small to large DP participants I talked. I mean, DP is very hard in this case since like the constraints are really high up. I mean, small to large, yeah. Since the constraints are, this is 10. The weights are 10 to the 6, but does that help? Does that help relating to the weights? The weights only go up to 1 million, which means that the that this is 10 to, yeah, 10 to the 6 times this. It's just too big. If you have like a path that all are like 10 to the, or like 1 million, and then this is like, maybe we could compress this somehow. Could you compress it? Could you, theoretically you could compress the weights, right? But no, but then k just changes completely, and calculating k is, I the aliens trick. I don't even like, know what was the aliens trick, but I'm just trying to figure out something that I could use here. The time limit is so small that I think it's just some conjecture where, is there, what is a case that disproves some greedy solution? Is there, what is this case here? These are the two nodes. Here 0 and 2, then this is 7, probably like the amount of nodes, and then there's 10. I would recommend you first look at the linear case. Yeah, I mean, yeah, the linear case. I haven't even looked up at the tree case. I'm just, this also just, I don't quite know how this would change, but what will be the difference between the tree case and the linear case? But I would just, yeah, okay, let's look up at the linear case. So the linear case, we will have some path. There will be some x and y without regard of its symmetry and these things, but then there will be some weights here, vi or something, and then for given k, so you want to give something to x, because you want to somehow divide k into two things, right? You give something that would benefit x, and you give something that would benefit y. And then other cities would be just like maybe too far and don't even matter. But I'm more interested in the following thing. If I want a city to open, to close at some time t, then this is kind of saying that, okay, this city closes at t minus w, where w is this weight between these two cities, right? Or other way around. If this city closes at some time t, this city closes at some time t plus w. But because somehow I have managed to come to here, this city adds the distance between itself, and essentially, if I want to include this city, it adds the distance between itself or x, or will add the distance between itself and y. Either this or this. We will pick, of course, the smallest. No, we will pick the closing time. Yeah, we will pick the smallest, right? Am I not correct? Like, wait, another conjecture. Ci is equal either to 0 or the minimum of the distance between I and x, and or is it the maximum? Is it the minimum or is it the maximum? At the end, this city should be reachable. It's the minimum, right? So it's either will be reached by x, or it's either will be reached by y. And this is the answer. It's either 0, it's not reached, or it's the minimum of these distances. Tell me if I'm wrong. So, okay. Yeah. The minimum of the distance between x and y. Okay, so this can be computed. This can be computed for everything, just a DFS, right? We compute this with a DFS. So we know each city. If I want to reach there, we know how much do we have to put in the effort to reach there, right? Because of the monotonicity of the function, of this function here, what will happen is the following thing. There should be x and there should be y. There's an LCA between this x and y, right? this, the LCA is a bump in the monotonicity of the function. If there is a node, then can we prove that this will be closer to y? No, not really. No, not the LCA. No, not the LCA. I mean, LCA is only related to some root node. But what will happen is there will be some node between x and y, such that this will be the break into the monotonicity. So there will be like this rise here. Then there will be like this. So here it will be the cheapest. Then it will go to the most expensive one. Then it will go to the cheapest. So this is like in a linear case. I'm talking about a linear case. But if there are branches here, if there are branches, the branches will go to more expensive and more expensive here, and here as well. So we're only interested in the path from x to y here, actually, and this path has some actually this is like not it's a unimodal function on this path, and since it's a unimodal function, um, yeah, okay. So we can compute many things, right? We can compute. Okay, and now because k is fixed, the sum of these things should be related to k, and since okay, so let's just take a look at this example here. Let's take a look at the example. So here, what I will say is that there's the minimum is 2, there's minimum 3, there's the minimum 2, there's minimum 5, and there's minimum 8 here, right? And since k is 10, the k is 10, right? Can I do this? Okay. So I'm saying that the minimum is 0. Let me just get a better 0, 2, 0, 2, 5, 8, 3, and k we said it's 10. So I can visit this one. I can visit this one. Of course, I can visit this one, this one, this one. But the assignment is what? What is the true assignment? City 1 is assigned 4. Wait, what? Sum of all closing times is 9, which is not more than 10. City 0, 1, 2, 3 are reachable from city X. City 0, 1, 2, 1, 3 are reachable from city X. This is reachable. City 1, 4, and 2 are reachable from this. Since this guy is reachable from both cities. Okay, so I see. Some guy will be reachable from both cities and thus will actually contribute more to its value. So yeah, so essentially this guy has 1 reachability if it's this, but then this guy has 2 reachability. So okay, so this guy if I choose that this is 4, if I choose that this is 2, it's 1, but if I choose that this is 4, it's now now 2 here valued, right? because it's not only reachable from this and reachable from that. So some cities will have, in fact, all of the cities will be reachable either from one or from both, or from zero. So all cities we have to choose here. And now the value that we choose, that we kind of choose here is So I see where the DP now here comes into play. If we want a DP here, we can see where it comes into play. So okay, so I have so we can look into the the linearity still holds, and now this would be now we can take a look at the difference, making this difference thing. Oh, not this. This is kind of makes sense. So this is one. Okay, so let's call something. Let's call something. I mean, implementationally, I don't know though how did I submit? How do I submit? How did I submit my submissions? Users. How do you submit this? You just submit a function. Okay, you submit a function, and this is the function that it is implemented in. So copy this. So let's just. This is the maximum score. Then consider some call here. Now this is kind of I think the problems from this IOI could have been better, Blogger says. This problem is not that bad. I think I don't know still how am I on the right path, but I want to implement just something, and but yeah, this is typical IOI problem. We would assume that there are monotonic things, invariants, and I kind of like that it's a graph problem though, because graph problems are quite more visual, right? But so I can use a vector outside of the function, right? I think I can. Oh, the second problem. Yeah, we're gonna read the second problem, definitely. Definitely we're gonna read the second problem. We have time. We spent like 30 minutes, 40 minutes, I don't know. But okay, so adjacency at now. What is this? How long are these? Okay, these are n-1 long, right? So adjacency at do I need to clear that up because this will be called many times? I think I have, right? I don't personally like this having this function, but okay, adjacency pushback v at I, adjacency v at I pushback u at I, and then oh, of course the path values here. What else we need to do? K is fine. X and Y, okay, they're fine. Now I kind of wanna just calculate the following thing. I want to calculate a couple of things. This is like distances, and this is at U, and so this is like at U, the parent, then there's like distance, D, something like that. Okay, and then we want to do distance, want to do distance at X I mean, I don't care about uh, I care about this. For V and for every adjacent pair of U, we're gonna, if V is the parent, we're gonna continue, and then the distance, and then okay, so distance at U dot pushback D, that's one thing, and then distance at so distance at adjacent, no, DFS at V, my parent, D plus W. Then I want to DFS from X with -1 and distance is 0. DFS from Y -1, distance is 0. Then I want to iterate over all of these, and I want to first sort the distance at I. Oops. Then say distance at 1 is my delta, so distance at no, distance at I at 1 is distance at I want this delta, and now I have some deltas, and it says, okay, I have some numbers. Now the problem, we boil down the problem into some numbers, where each number, if I take some number, I need to add them to K, to the, but no, is that the case? Yeah. So from each of these distance vectors, I need to choose whether, oh no, I can't do that. Oh, we can't do that. Oh yes, link to the problems. Yes, I'm sorry. These are the problems. These are all the problems, and we're taking a look at the first problem here. So I'm trying to boil down the problem into saying that okay, we have some nodes, and we can either take the distance from X or the distance from Y, right? As we either we assign this, so it kind of looks like one more graph problem, like a matching thing something. Like if I have like a flow, but it's not really is it a flow, or is just it's bipartite? It's not bipartite. Okay, so imagine all of these are nodes, all these nodes, and the maximum flow that you can have here is k, right? You can push k flow, and all of these nodes are either to two things. Are either the some distance from I to X or distance from I to Y. So this is like a flow here and a flow here. You have this for every node. There's like infinite flows here. Could imagine that. And now we want like the minimum. Not the minimum. Yeah. No, this is discrete, so you can't have a flow here. You can't have a flow, yeah, of course. This is discrete flows. But it's fun to imagine it like this. This is discrete. So you pick either this distance or this distance, but can we do something clever? Let me think. Something clever. You can't pick both. Well, actually, you can pick both. Yeah, okay, yeah, I see. So here, let's say I have 2 and 4, right? This will be one of them will be definitely bigger or equal to that guy here. That guy will make this, but then the delta difference can derive one more thing here. And why can't I do just the delta difference and greedily pick things? Is it that doesn't work? Why can't I do that? The delta difference will get you one more thing, right? I'm just interested in this. Yeah, I know the solution. I'm just saying. I know practically the solution is very big, probably, but I'm just seeing what it will print. What is going on? Wait, what? Oh, the DFS is wrong. Something. V U then A plus V. Oh, of course. Probably disprove this, but I don't know if this will work for the linear. I'm kind of want to see if it will work for the linear case. Should the main be with nothing, like empty here, or can I print? This won't work, of course, but I'm curious how big of acceptance it will get. Wrong answer on all of them. But why? You test out for the first case and you don't check others. Okay. How do you disprove something like this? The 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 delta difference will wait. The delta difference will be. Oh, I see why this is wrong, because the delta difference cannot be reached if. Yeah, of course this is wrong. I mean, the delta difference cannot be reached if it's not combined with this difference. Yeah, I see. Like it's very interesting. This boils down on this kind of boils down if you have something here. All of these can lead up to some other thing, and now you have to compute that this first, then this, and that's why here maybe it's some kind of a DP or something. Wait, I sent you a Discord zip file. The problem with the starting code and grader. No, I mean, it's fine. It's fine. I will just submit here and be. Well, the linear case. I don't know if I should bother with the linear case. I'm interested in the other problems as well. I want to read them, but um, the linear case. Does it? This is also. For this case, where the sum of n goes up to 20, this is doable in like 2 to the 20. You choose whether you get from X or from Y or something like that, and then and this is doable. This here could be some DP. This here could be also some DP. But the linear problems as well. Some other. No, I believe there's some greedy solution in the fact that no, of course you can't do that, but you can maybe divide them into two and then binary search over like how many things. The formula is like if I spend some y and then d to get that, or I spend y. I spend 0, I spend the distance between I and x, or the distance between I and x plus, or the maximum, of course. Where x and y, we don't know that here. The maximum can be rewritten as, so this could be rewritten as like the minimum of d and x and d and y, and could be rewritten as the maximum, the minimum plus some delta, of course. The minimum of this distance and the minimum plus some delta. And now if you don't have, if you want 0 points, you get this, like a knapsack problem, like essentially like a knapsack problem. You want 1 point to get this, and you want, but not an, and you want 2 points you get this also maximum of this. Is it? That's the maximum, right? Yeah, so you want 1 point to get this, and then you want 2 points to get this. And what does that tell me? That kind of tells me that is quite interesting that we have these two things here, the minimum or the maximum of this. But I wanted relative to this. I wanted it to relative to this to be able to do this, but like DPI of interesting. Okay, I will read the second problem right now, and I will think about this. I'll think about this is again a tree problem, which is quite unusual. They forgot to plan the trip, but maybe it is not yet too late. There are n landmarks. Some pairs of these landmarks are connected by bidirectional roads. Each pair of landmarks is connected most one. Organizers don't know which landmarks are connected by roads. We say that the density of the road network is at least, what is this? No, this is gamma, right? If every 3 distinct landmarks have, so this, or is it delta, or is it? It's delta, right? It's delta. If every three distinct landmarks have at least delta roads among them. For each triplet of landmarks, among the pairs of landmarks this, and this, at least delta pairs are connected by a road. Wait. Let me try to understand this. The organizers know a positive integer d such that the density of the road network is at least d. Note that the value of d cannot be greater than 3. Among these pairs, so this most 3. The organizers can make calls to the phone dispatchers and to gather information about the road networks. In each call, two non-empty arrays of landmarks must be specified. Oh, is this an interactive problem? In each call, the two landmark arrays from 0 to must be specified. Landmarks must be pairwise distinct. Yeah. So you need to match them. For each call, the dispatcher reports whether there is a road connecting a landmark A and landmark B. More precisely, the dispatcher iterates over all pairs ij. If for any of them the landmarks A, I, and B, J are connected by a road, it returns true, otherwise it returns false. A trip of length L is a sequence of this where are connected by a road. A trip of length L is called the longest trip if there does not exist any trip of length L. So you want to find the diameter of the tree, right? Want to find the diameter of the tree, we can give two arrays where the I and j are equal to. So for any of these pairs, for us there will be a specification where more precisely it iterates over ij. If for any of them the landmarks I, AI, and BJ are connected by a road. What does that mean by a road? Can a road be... Is the road just edge? Or is it... Or, so no. So it's only an edge, right? Because there are... Some pairs of landmarks are connected by bidirectional roads. Each pair of... But it's not a tree. Is it? No, it's not a tree. Of course, it's not a tree. It doesn't say that there are n-1 bidirectional roads. Okay. So if you have a graph and you want to find the diameter of this graph, not the kind of the diameter, but the longest strip would be from y1 and 5. What is 1 and 5? Longest strip. Oh, numbers and then the density of the minimum density. So d can only come into 3 values, right? So d 1, 3, 2, and 1. Okay. And then the condition is that the queries are how many points you get. N is 256. The sum of n does not exceed 1000. Wow, that's a bad problem. That's a lot of like math here, like edge work. Start so far. While removing the int main changes. No, this is definitely not the better problem. I don't, if like you need first to break down the problem into these three different D cases. So one case is where, so the minimum guaranteed that like all of these are connected for each triplet UV, and W is connected. This, if this is the case, if D is 3, if D is guaranteed to be 3, then the whole graph is is it a complete graph when D is equal to 3? I think it is, right? I mean, it doesn't mean to be complete graph, it just means that, wait, what does it mean? It means that this is a complete graph among the pairs. So yeah, so if D is equal to 3, it is a complete graph, right? That's observation number 1, right? Observation number 1 is D equals 3 complete graph. Am I crazy here? Complete graph. Yeah, of course, of course. When it is a complete graph, you could do whatever you want. The longest, what do you need to even return? Just so huge task that I don't even know what you need to return. Longest strip are connected. How do you return that? What do you, wait, to here you return, this to help find the longest strip, and so yeah, so of course return the, no, not the distance. This here is like you return the trip itself, as I understand. You were right. You were right from the beginning. Yeah, you were right. So the complete graph. So that's correct, and then that's solved task one. So what happens if these two? What about D2? These two, it means that for every triple, one of these things are connected, which means that two of these things are connected, which means that the whole graph is one component. Could be proven with induction. If it is one component, I'm just not now I haven't haven't even thought about how I will query how what calls will I make, you know. I'm now the thing is that if n goes up to 256, if n goes up to 256, it's there. I can query about, wait, Yeah, you query every pair, but every pair is what? N squared. Wait, you don't need in subtask 4 your score is determined by the. Wait, you don't need to the queries don't matter in subtask 2? Is that the case? That the number of queries don't matter? Yeah, okay. If number of queries don't matter, then yeah, of course, every pair could be and just construct the graph like that. Okay, and then just a DFS or a BFS, right? It doesn't matter. You can even start from anywhere and just try everything. So yeah, okay, so that's easy. These two things here. But then D1, what happens D1? D1, there can be multiple components right now. But it says that it is, so D1 it guarantees that there will be some connection here. But now we don't care about this. Now we care about how do we compute more of this? How do we know this? Can you break it? Well, if so, the best queries can be even done up to 400, which is quite incredible. Okay, I'm thinking about multiple approaches, but one approach is okay. Let's fix one thing and try to find like an edge, right? But that's okay. So that's pretty straightforward, and then up to this query should kind of work. 256 times 256. Well, do you get all of the points? So 256 times 200. No, you don't get all the points. Okay, so you have to be a little bit clever. Of course, if one is connected, then you don't need to try. This is exactly the number. So yeah, so this goes up to n squared. So I can get what is this 35 points with n squared approach. Yes, exactly. So 35 points. Okay. Now we need to go a little bit better. And can we do something? You need to find the longest strip, right? The longest strip. So if there is some trip that is shorter, the longest strip, there could be multiple longest strips, of course, but interesting. It's possible in 400 queries. This is incredible if it's possible in 400 queries. What is this? Log? It's 8, right? 8, even 8 times this is too much. Okay, let's divide them somehow. Let's divide them somehow. If I take some, it's enough one of these two. What if I take half and half, and I take the other half? Let's say that there's connection, that's true, and then I slice this here, and there's connection to here and here, and I slice this here, there's connection to here, here. So there's like, for this and so for n half, I will be slicing down times, so this is 2 to the 7 times 8 to the 3. This would be to the 7 there times 2 to the 3. I'm slicing down, and there will be some connections. And then there will be more. So wait, I have 35 points, right? If I go okay. Then you binary search something. Really, I think it is like 2 chains. 2 chains. What does that mean actually, 2 chains? Like if you keep dividing it like this, no, you want to divide and conquer, but you want to divide and conquer not like this, like in n half, but you want to divide and conquer. There's some like mathematics here involved in how you would divide this. There's some minimization function that you need to. So you would divide from 1 to n. You would divide it in a couple of pieces. Then try to divide these further. But then you need to figure out how much is optimal. So what about square root of n? So square root of n. What is the square root of 256? 16. 16. Oops. 16. Okay, so let's divide n in blocks. Let's divide n into 16 blocks. And then each block will try to figure out how it is connected to some other blocks. Okay? So there are 16 blocks times 15 divided by 2. So how much is this? This 8 times 15, right? 120. So in 120 operations, I can say which block is connected to which other block. Then inside of the blocks are some connections, but we don't care about these connections because well, we care about them, but we can deal with them a little bit later. So the blocks, how are they connected? Inside here, there is at most 16 other things. So there's at most 16 other plus 16 other in the other block, so there's 32. And then there is 32 things, right? And then there's oh, you want to find the longest path like this. So, okay, so we figured out that if we divide them in blocks, how much is cubic root 256? Um, okay, we divide them into blocks, and then inside each block we can further ask how are they connected, and then this is 16 blocks times 120 if we want to connect them, right? So that's quite a lot. But if we have 16 blocks like this, isn't it more think that like is it very possible that they are actually very connected? I think there's great probability that a lot of them are connected as well here. And this doesn't really help a lot. Bidirectional. Yeah, this doesn't help a lot. Wait, is this the maximum? Let Q be the maximum number of calls among all invocations every time. Wait, doesn't that mean that this one does not 1024 this kind of makes it half of the length. So these blocks can be like really tightly packed together, and then that doesn't quite help if they're really tightly packed. Mm. Wait, what about if I start from one position, then there could be like I can start from one thing and then I can go Okay, the probability that this disconnected is very high. So it's something to do. For each n, let me try something like this. Let's try probabilistic approach. For each n, 256, I will take a window and I will shift it some amount. And then it shows me how it is connected. Like let's say this window is 256 divided by what? Let's say times 16. Let's say a block of this. How much is this? 4,000. That's too big for window. Okay, let's make it times 8. 2,000. We're gonna shift 8 times some window. Probabilistically. And then but that tells me how it is connected to some other things, but doesn't tell me anything about the path taken, the path that I need to return. Does it have to be in what? Wait, what have do I return here? So it should return this. Okay, so this makes quite a hard problem. I don't know how is this an easy problem except like just solving for some subtask and hoping for solving this for 45 points. It's not even easy. The queries are too little. 400 queries, and then I don't understand one thing. In subtask 4, your score is determined based on the number of calls over a single invocation. A single invocation. What kind of binary search will you do here? I don't understand. I will just do either a square root or like a cubic root decomposition or some mathematical maximum, like you have some function and where you want to pick up some blocks where these blocks are the most because 256 is practically no. So you have like connections over the blocks, and what does that mean? That means that means nothing. Like if I have connections over these blocks, I know that the path will go from some point like I can probably say that the longest path connecting these blocks, like the longest path connecting these blocks will be a not really a part, but like it's very likely to be, but there could be a lot of these connections, and that was what scares me. Like, what if all of these blocks are connected with each other? Like this. Everything is connected with everything. Then you have no clue how to start. You could divide one block here. Let's say that you divide this block one more time, and then you, like, internally, what if you know everything about this block internally? Let's assume that you know the whole structure of the block internally, how these are connected, but you don't know how they're connected like that. So still, you're quite clueless. Okay, let's say for each. Okay, let's say this trick. For each, I will sort the positions. For each position, there's some binary thing here, right? I mean, each position will be denoted by some binary number. And each position can be matched with some other position. This. Then you want to say that okay, let's say that I will pick all of the nodes which have the first bit on. I'll pick all of the even nodes. There are 8 bits in the position, right? I'll pick all of the even nodes. Or, yeah, whatever. All the even nodes. First bit off. Then are they connected? Okay, they will be, it's very likely to be connected. It's very likely. Then there might be a bit where can we construct like a tighter bound? There might be. If I take all of these bits, like, okay, I know that let's say they are connected. Then I search for this bit. If it's on, are they connected? And let's say that if it's like off or on, are they connected? Then I search for with constraints with this bit, on or off, are they connected? But these are already bits that have been. Wait, there's 256 things I can search, right? 256, and I will say that the following 250. Yeah. Okay. Let's say like this. Each position can be represented by a binary digit, right? By a binary number. But let's say we have a mask, and we say that some positions are fixed and some are not. So we will do, let's say we fix 4 bits and 4 we don't. We iterate over all of these, which these are, how many are they? 16, right? 16. So this we fix. Let's say this is our fixed. We iterate for all of these. And these here are all, I say that these are fixed and these are not fixed. So we have blocks of up, so we have 16 blocks in this way. Right? But then what if I fix the first? So there's what, 16 questions here. What if I fix the first and like I don't fix the other ones? Like something like this. And then okay, so there's four things here times 2 to the power of so times 4. So 16. So here there's 16, here's a 16. Here's will be like 16 with one of these. So yeah, so 16. So these here will tell me will break them down. This is essentially 16 times log of 8. Or something. And then when we have this is what? This is so there are 16 boxes here. Here there are more boxes. And even more boxes. But then this way you eliminate things. You start from the from having small amount of boxes, and then even smaller amount of boxes, and even small small amount of boxes, and more boxes, and then more boxes, and then more boxes, and then you just mask them like bits. So I think something like this is the solution here. I don't know what's the real solution, but I think it's some idea here of this. Plugger maybe will tell me if he's still here. First you start with, okay, like start with one box, then start with like 2 boxes, and start with like then with 4, then with 8 boxes, then with this. Then now you know that if here there's a connection between, like if here there's a connection between here and here there's connection, and but here there's no connection, then you quite certain know that this here is a component in itself, and this here is a component in itself. Or it doesn't know the official solution. Now the problem here comes to, okay, so these are like really small amount of queries that you probably need to take up. Because the last thing we don't even look. I would think this is small amount of queries. But then now the problem is, okay, let's say that this here. So essentially each box will be divided by some fixed and some unfixed. Yeah, how do I divide the box though? This is quite not easy. So let's say that I have some box, that these bits are fixed, or let's say that these are fixed. There are 16 such boxes, where these bits are fixed and these can rotate through every of these. But then what happens if you fix these bits here? That doesn't help, right? Because each box here with fixed, each box here essentially fixing some bits and unfixing the others. This box is, but you could always divide that by 2 here, and then this box will be like divided. But maybe it's not the 2, maybe you're supposed to divide it like very cleverly, like this, where you fix some bits, you do the others here, and then the others here, or some mathematics here. But so let's say that this box, is in half here, connected with some other half, and this box is connected with some other half. Then let's say that this box is like that, and this box is like this. We know that these are two halves that are connected, which now begs the question: is it this connected with this, right? If it is, it means that the longest path that goes, I mean, not the longest path actually, but somehow this is connected to here, and somehow this is connected to here. And now if this is connected like that, the longest path that is, it either goes like this inside this box and then inside here in some way, or it goes into this and inside here, or inside here. It cannot, it can go like that. Well, no, yeah, that's a bad one. There is a path Let's consider that these boxes are like that. But because it's a graph and it's not a path, it's just so hard to work with. Hmm. I don't know. Let's look up the scores just. There are a lot of people who solved it for 60 here. This problem. Oh, 60 is a quite. I mean, 60 is quite success to solve this. 60. But to solve it for 100, that's impossible. I don't think so. I don't even want to look at this, the third problem, how difficult they are. I won't even look at this. I may call it just a little bit for the first and the second problem. Let me just see, what did you do on the... So third, I know, this is the problem. Yeah, I mean, yeah, just it's a stupid problem. I like the first problem a lot better. I mean, it's much more. This involves some mathematics here to come up with a game strategy, and these are not really my favorite problems to come up with these strategies, since so for 60 points, okay, you solve this here and you solve this here, okay. So for 3 and 2, right? It's fine. But then for 60 points you have to solve this here, or you just solve this one, right? The second problem is that, and because of that I didn't get the first subtest but got the second one. So you didn't got the first test but you got the second for d equal 2? And this n half here, I could say that a randomized maybe approach should kind of pass. Just trying out random, but maybe no. Trainer. No, the third, on the third problem. I mean, the third problem. I don't know. I don't know what this. So okay. Let's read it just for the sake. I have time. Square-shaped forest located in Debrecen or whatever, and by themselves. In the forest, each cell is either empty or contains a tree. At least one cell in the forest is empty. Okay. The famous sports club of the city is planning to build a new soccer stadium. The stadium size is a set of distinct cells. Formally, this means that for each cell is empty, and at least for each ij through S, at least one of the. Okay, this means that, okay, yeah, okay, that I understand this. Soccer is played. This means that all of these are distinct cells, right? Is that what it says? That for each ij, for each pair ij from 0 to S, at least Ri or Rj, or this is the different. Soccer is played using a ball that is moved around the cells. A straight kick is defined by either following two actions: move the ball from some cell from Ra on the same row, where all the cells between Ra and Rb in the row R where the stadium contains all of the cells. So yeah, so okay. The stadium is regular if it is possible to move the ball from any cell contained by the stadium to any other contained with at most two straight kicks. Huh, interesting. Okay. For example, consider a force. Okay, blah 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 blah. What is this? The sportsman wants to build a regular stadium that's as big as possible. Your task is to find the maximum value of S. Okay, so first we need to define what is the invariant of uh, a stadium that has two kicks. So a kick in one row is fine. So two kicks, it means that at any point could be. So you cannot have a polygon which has something like this, because from here you can't come to here, as far as I understand. With two straight kicks. All that the size is regular. So this here is regular. This here is not. And at least three cases need to move. The stadium on the right is not regular because it's impossible to move. Here it's not connected. Okay, so there are this matrix given. The matrix is 2000 by 2000. Okay, so you could. Okay, so what? Okay, what kind of invariant does my stadium have? My stadium has an invariant that the regular stadium. We need to find what invariant does it have. It can never have this. Or some more complicated. So a bulge. How is like. Okay, so it doesn't necessarily have. Yeah, it doesn't have to be con. So if. Not a convex, but what is this called that it doesn't have this? The angles here, the sum of the angles is important somehow. Somehow the sum of the angles is very important. So if I go here, there's, okay, so there's left, there's right, there's left, there's right, there's left, there's left. So left, right, left, right, left. But what bulges have? So the right is essentially for 3 lefts, right? So each right will denote 3 lefts, which is correct. What does a bulge have? I mean, it's the same, I think, right? It has to be the same. It has to be an invariant as well here. Right, because it's a convex, right? So, but what does the bulge have? Left, let's start from here. Left, or no, let's start from here. Yeah, let's start from here. Okay, so you here, you go from this direction and you go like left here. Then you go left. Then you go right. Then you go right. Then you go left. Then you go left. So left, left, left. And then left. So this right is responsible for these 3 lefts, and then this right is responsible for this. So you have right here. So this is a bulge right, where you have like right. You cannot access this here. So essentially, we want not to have that. Okay, n is 3. N is 3, probably called some brute force thing. Trial to the some. But that's so n is. There is at most 1 cell containing a tree. There's most 1 cell containing the tree. I mean, okay, cold forces problem, BC problem, where you have to find all the possible configurations if one of the cells is a tree. This is quite an implementational one, or this I don't know. Okay, so you can't do left right like that. In each subtest, you obtain 25% of the subtest score if your problem judges correctly whether the set consisting of all cells is a regular all empty cells. 25%. Wait, you can get 25% of the subtest score if you're, so you can get just for judging it. More precisely, for test cases contain solution gets full points if it returns the correct answer, which the size gets 0 points. Otherwise, for each test case in which the set contains all cells not a regular cell. Any other value. So if you judge it that it's not an empty cell, that is not this, and then how do you do this? Well, what if there is a cell in here and you want to build a stadium like this? Then you cannot go from this point to this point. Which one thing proves that if there are a lot of the fixed cells here, so you just have to take a look at. Right, if you have one cell like this, corner cells are fine, but as soon as there's a cell like this or there's a cell like this, it fails. There are multiple cells like this. Can there be a cell like 25% of this? Okay, this is quite interesting. This we could work on. but judging this, I would say that judging it by the it's starting raining. Time limit. There's a lot of time. Okay. So if there is a cell, I suppose something. I suppose something like this. Wait. If there is a cell somewhere in the middle, the stadium, there are multiple cases, but either the stadium is bounded like this, let's say, either the stadium is bounded like this, so the stadium could be bounded, of course, with all these four directions, but let's just assume it's like either this cell is like in the corner, this cell is in the, so if n goes up to like 500, we might be able to iterate over, but no, we are not able to iterate. If n goes up to 30, we are able to iterate over all of the possible rectangles in which the stadium might go. But then you see this cell, we can take the whole rectangle here and we can say, okay, this cell prevents us from going here and thus kind of eliminate this. This cell prevents us either from going here, making this, or going here. So in other words, if I have a matrix and I fix some rectangle, I want all of the empty cells, all of the non-empty cells, all of the things that here, if like we want none of them, or actually no, we want like more. You could have something like this, but like let's say that there's some cell here. So for each cell here, I need to kind of say either this is all forbidden, either this is all forbidden, this is all forbidden, or this is all forbidden. And now depending on the situation of how they are all constructed, then we forbid some space here. But then there is another problem, and in fact it has to do with this. Let's say we forbid this space, right? Let's say we forbid it like this. So this is not in our stadium. Let's imagine that there's another cell here. Then there's no way to forbid this. Or there is a way. There is a way to forbid this, right? Actually, yeah. So you could forbid this. You could, if there's a cell here, you could per this. Because you still can. Oh, but this now doesn't work. Oh, so here's the idea. So this is a constraint, one more constraint that you have to take into account. But forbidding a cell like this there, you cannot then forbid a cell like this. For all of this here, for all of this space, you have to access it here. So you kinda, this cell here kinda forbids this whole region. Because you have to access that. And now if there's a cell here, actually it doesn't forbid this whole region. It's not, it just says that here in this region there cannot be a cell. Wow, this is insane. So it says that not only that there's a region that we need to subtract, but there's a region where there cannot be a cell. So given these 2 points and given some cells inside, so there's, okay, so there's let's say there's 30 points, 30 by 30, right? All of them can be the starting point and all of them can be the ending point. So that's 30 to the 4. Then you need to iterate over all of the points here inside and do some magic. That's one way for this subtasks. But then there's stronger subtasks. Taking this into account. So not only that there's a so you cannot. So here, if I forbid this here, if I forbid these two, and not forbid these, there could be a way. If this had been here, then forbidding these 3 would not cannot be reached, these two. So there's a mathematical shape that can be described by how this shape has to look. Would you agree that the first problem is the best one on the first day? Yes, yes, definitely. I would agree that the first problem is the best. The second problem is quite I don't know. It's they're all interesting problems. I'm not saying, but the second problem involves some kind of strategy, mathematical strategy to solve it. The third problem is just like some geometry. This is like the geometry, some invariant with this, how we forbid it and how we don't. The trick is here. Okay, we can build a prefix thing for the second problem, this here, and we kind of can query anything in all of one, right? So we can query up the sum, everything here, or we can, but it reminds me also of some DP problem, let's say, if some kind of a DP thing here. But since you can see that a lot of people didn't even succeed in solving like some percent or some like how much will you get here? Will you get like, here you get 30 and then 48 points. So 48 points for the so 48 points, but if you get 48 points in this problem, you're already very, very good. So about how much did you get the first day? 42. Damian 90. So he solved what? 24 points. What is 24 points? 24 points is. What is 24 points? For what cases is this? I have no clue. How do you score 24 points? Like, I mean this and this, but doesn't make sense. How you can't? Can you look that up? How do you score 24 points? Oh yeah, you can look it up. So on the subtask, what is this? Soccer stadium subtask 2, you get 8 points. So there are half points. So he scored some half, some this 25. He just checked if the conditions are right and scored a 25%. Okay, 25%. Subtask 0, one tree, one empty, one subtask 0, there's at most one cell containing a tree. This is quite easy. This is quite easy with one cell containing a tree, because if it's like inside, you just want to compute, like, I mean, not quite easy, but it's called forces problem. You want to compute the area here where, like, if it's inside. If it's on the edge, you want just to subtract some area here, but it's quite a okay. So this means 6 points, and yeah, there's at most one cell containing the tree. What about, do you have any other invariants that you found for the third problem, like how the structure should look? Wait, what if there's a here and a here cell, right? And then, okay, so let's say you want to do this, and you want to do this. You can't come from here to here. Does that mean that here is also forbidden, or here is also forbidden? So because this, you cannot come over here. What about you do this? Can you? This kind of resembles some like you have these here that what if you could prove that this is some kind of uh, about, do you have any other like invariants for this problem? So it kind of looks like the shape will always be constructed as some kind of this thing where all of these would just limit you to somewhere here, because there's no way that there's quite not useful to limit it like this. maybe it is sometimes. Something interesting I should mention: on the second day, on the third problem, for the full solution you had to use at most 7 colors, but one of the competitors managed to come up with the idea that used 6. I mean, come on, like the third problem. We're talking about the third problem on the second day. Wow. I mean, but no one solved it. Third problem, second day on the third problem, but no one solved it full, as far as I can see here. Even this guy that solved it, it's like LGM or something. So they all like solve it with different submissions for each. Okay, this he solved with different submission. Let's see. This is something 100, 60, 30, 18, 22, 8, 6, 0. There, yeah. So he solved it with like one submission on this problem with full scores. That was after the competition, but wasn't I asked. Okay, okay, yeah, okay, that makes sense. Tanaka got 0 here on the second day, but still managed to get so much. Yeah, I mean the problems are really, really difficult. I don't know, like I think the shape should look like this. I think the shape should look like this somehow. And now how the thing is that moving this line here, moving the boundary one step at a time, only changes few things. Only changes few things, but doing it in linear time is is practically like I don't know how is this even possible, doing it in linear time. Uh, what are these shapes? These shapes here, how they can be? Well, and why do you choose this? Like, and how do you decide? You start from the center and then you go to the side. But no, doesn't make sense. Do DP maybe. Well, this is convex here, like this, but still doesn't make sense. I mean, yeah, sliding ring. That's the only. Yeah, I would think there is something idea with sliding window like this, and since this kind of thing is convex here, and other things here will be convex as well, like that, like a circle. Some things will be added, and then some things will be removed from influence. But the only thing that will be removed from influence, like no, here it will be changed. Sometimes it will change. I haven't looked up the solution because I'm relaxing a little bit. Yeah. I mean that's pretty good, pretty good. just to relax. I wanted to look up the problems because I was really interested in like why like these are really difficult problems. I mean, that's not maybe, yeah, like I don't know how the second problem is. There's some strategy for the second problem, but I would think the first problem is quite okay. Then for some subtests for the second, and the third problem, maybe just the 24 points is just quite, I think, enough for the third problem. Anything more than that, and you need to really put on. You can see like people that got a lot of points on the third problem didn't get nearly 0 points in this until you go for like the silver medal stuff, and where you have, I don't know where are these. Yeah, this is silver already. So the second problem. Okay, we kind of, okay, let's recap. So the first one, the reachability, quite an interesting problem. Quite an interesting problem. And it's interesting that I think it's very interesting on this idea. The minimum of, so you have, either you choose this, so for each of the DFS, for each of the nodes, you either have 0 points, you either choose the minimum cost, so the minimum thing, and you get 1 point, or you choose the maximum thing and you get 2 points. I thought that you could do something with the delta where there's 2 points because it's kind of fixed. You just what if you go like over, like first you give the minimum, like what if you do something like some stupid like things like this. You push into the like priority queue, you have some like priority queue, and then you insert first like minimum of this, so minimum things, and then you insert like what I is this, and then okay, so you pop from the priority queue, and then when you pop something from this thing here, when you pop from some top, you then insert the maximum, and in the same thing, or if you pop the maximum, you don't do anything, and in this way, can this greedily work? I mean, can you get at least some points with some this approach? I mean, you say it's 200 and something lines of code, and this kind of scares me because I'm not planning to write this much code, but I don't quite know why this doesn't work as well. I mean, probably it doesn't work. Yeah, I would assume so. I would assume so. I will just write it here, just so for fun. Yeah, probably because there's this idea of, What is this now? Insert push. Okay, so let's say this. Say it like this: while PQ is not empty and K is bigger than PQ dot all dot first, then insert plus plus if listed at so auto weight and V is PQ dot top, PQ dot pop, visited answer is visited V is 0, PQ dot push. I'm thinking about is this conjecture true? It has to be. Because this maximum here will never be reached. This minimum will never be reached until another minimum prior to this is reached, and thus making it quite impossible to. Yeah, but another thing has to be careful here. One more thing has to be accounted for. The distance between another distance has to be accounted for. This is the distance between x and y in this manner. So this has to be accounted for. Distance, then this distance, then I, then the operator in which if distance is other distance, then di Now here we push the minimum of this distance. Now here we then di is of course we don't push the minimum, it's okay if distance of I0 is smaller than distance of I1, then PQ push LL distance of I0, then the first is smaller than distance of I0 dot second, Yeah, so if this is here, then we need to do this. Yeah, that's second, and then this is I. Else, now here's the push one, push one. Yeah. Okay, and then this is accounted for. So that first dot d, not that first, that dy. So it's more than what we can pay. And then of course the answer is get this. Then this here is of course what is this dw, di, and I itself. If I is visited, then we want to push the other way around, right? So this want to push it like that. Then return the answer. Of course. Pick it up. Oh, of course, K. Push the... Yeah, so now the maximum distance is not here what we want to push, but we want to push like the difference between these two, right? Is that the case? I think. Oh, I see. No. This is, yeah, this could work, but this could, we have to be careful about where do we start. Yeah, I think this should work. But wait, why is 7? Why is 7? Okay, visited, of course, uh, visited at I is now 1, of course. I mean, this one won't be correct. I don't think this would be correct. I'm just submitting it. It shouldn't be. I mean, it's better than previous. What is this batch 2? Batch 2 is what? Batch 2 is linear? Oh no, not longest strip. Batch 2 is... let's not make this mistake of using long longs. Yeah, so it's not long longs. But what is this? What is batch 1? What did we solve? It's guaranteed that there's no this. Why? What makes a problem with when there is something like that? What makes it a problem? When this is then further visited, you just want to say that this never changes. Then pq.push, you push the reverse thing, so the this is bigger, then you push this difference where this. Yeah. The problem is this. I think. So we want the smaller weight and we want the smaller distance. Yes, if there are two things and then you push in from the smaller this. Wait, this could be the smaller distance and yet they haven't reached there yet. I've never thought of this. What if this is the smaller distance but they haven't ever reached there? So you travel from X, you travel from Y, right? But let's get to some point here where this distance is equal. But you haven't. When this distance is equal, then there exists a smaller distance such that this is the case, and then I think wait, what? Can't I prove that? Consider a city, aim with some. The distance at second. So the distance second is this here. Oh, but sometimes maybe can it be possible that there is a more worth than this to access this distance? Yeah, but this never happens on a road. It actually happens, do happen. Okay, so to avoid to make this kind of work, we need to prioritize also things that are inside the path, inside X and Y. And this should work for everything, I think. Yeah, because there could be something other, but then there's no way to prove that there's. Yeah, prioritize things that are inside the road network, and then inside between X and Y. In case of equality. In case of both of these equalities, then we prioritize things that are inside. Okay, let's. Okay, let's say that we have LCA, and then this is adjacency list where we want to put here adjacency. Okay, so let's say it's like this, and this is here, this is distance. Doesn't really matter. And then there's like on path. And now I think I already have this computed somewhere. So this under means that this is ancestor. Is ancestor, and then U and V. V is under this, so this is V and U should be different here. V, X and V and U and X should be the case. Now here adjacent, and then root is 0, doesn't really matter. And then you need to prioritize here if this is and this, then return that LCA on path. What is now this LCA? You can't access this LCA from the operator? No, I think you can, right? LCA dot on path. Or no, you can't access this. Well, the thing is that you don't quite, you return is like, you return this on path value here. So like return that my thing is on path. So this is like the other way around. You want to return something that is on the path. to something that is not on the path. And now to construct this here is like saying that LCA on path from X to Y, and this I is I on the path from X to Y. Also, here's the case. I don't care about this one thing here. I mean, I don't even know if that's... No, that doesn't work. Is it correct? If it's on the path, then it means that this is correct. This is yes. Then we want this to be... Yeah, I want this to be small. So between X and Y, 1 and 0, 1 and 2 are on the path. Let's see. Between X and Y, 0, 1 and 2 are on the path. And others are not. So first it's prioritization of the on the path. Yes. But I want to try something. Let's say like you want me to send an example that it fails. Oh, but isn't that example really big? Like I prioritize things that are on the path, since this will gain me more things later. I mean, you could try sending it. I can check it out. And prioritize things that are on the path, and then I mean this doesn't need to be. I mean I think this should work for the linear cases, for all of the linear cases, but maybe I'm wrong. I don't know what actually happens on a tree. I'm just looking it up as a linear thing. I'm just gonna pop it in desktop to see what happens. Oh, this is really big. I see. It's linearly... Oh, it's not actually that big. I don't know if I want to look at the code. Just let me see. Like this is 44, right? So I can't even read this. This is like, why are they not given up in this format so you can read them? And then K is pretty. Well, this is 0 and 49 are X and Y. So this is kind of interesting. So 0 and 49 are X and Y. And then all of these things are inside. So that's not the problem. That's not the problem. But they match up somehow here. So they match up that you could maybe all buy them all or something. No, 44. You don't buy them all. You have something left. 44. What does 44 mean? Wait, does it mean that? Hey, it could be quite wrong here, right? It could be very wrong. Like maybe buying something here will cost you more, but then this will cost you even more. I don't get this. Should we write like should we write like a reader for this? Let me save this inside this. No, competitive. It's competitive. Okay, let's save it here. Should we write a reader? Okay, let's do this. NXYK, and then we want to write zone edge. Just write a simple. Actually, what I'm doing here? Let me just U, V, and W. All of them should be n minus 1. Huh? Oh, 51. This is way bigger. It cannot be 51. This is because we buy something. Right. In the distance we have pairs of LL. This here D and DI, and then we buy something for. We push this here. If the first is smaller, then the But wait, we can't do that. Well, we can't do that because this is not possible, right? Yeah, you're buying it like this, which is not possible. This is not possible. What am I doing? What am I doing? It's you can't buy like this. Oh, this is stupid. Okay, this works only if for the first batch. Of course, this will fail for now. Come on, like convex. I know, but like I know that something has to be convex in this here, and the function looks like this. But wait, what? What is this conv? Wait, don't. No, 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 no. This is no. This surely cannot be it. Okay, so first, wait, what? This solves the. Okay, so he pushes DFS, okay, and then he finds the path from X to Y. And he says which of them are inside the path, then these are like kind of these are what we decide on. The other things are not really that bad. And then if it's not on the path, we push the distance to this or the distance to the other thing. We make sure that this is the smaller distance first. Then we solve for using some things. We solve for so for all of these other things, for all of the things that are not on the path, convex and concave. So what is the convex function is how this, okay, so we built on the implosion. So like this on the input, like we oh, so this is essentially saying that if 2a is bigger than b, it's saying that of course this can be in convex thing because like we will choose always like some a here. We'll never want to choose b. And there's the concave, and then uh, convex function is what we just sort them. We add on top of that, and the answer is on every odd. Can't even. Ah, it's hard. Do concave. Okay, so he just he even for the things that are outside, even though these are like functions like this, actually like oh I see. functions that are but he loses information from where do you gain this function. Here, when he swaps the things that are outside, so these are like outside, he swaps them if this is bigger, and then this loses the information of it is the distance to one or is distance to the other. But okay, let's say that this is solved. Then there is things that are inside of these, like inside the from x and y. And then the things that are inside from x and y, he binary searches where he binary searches something. So he binary searches where is that like limit of where you put the total, where you switch. But then there's S1, so the size of S2 is what? The size of S2 is this, like inside, the path inside. And the size of S1 is this. He wants to current sums for each of these. The size of the paths doesn't change, right? Is it? Oh, this is some edge case. So this is some edge case here, where you take everything here and you take some distance from something from S1. What is this? S1 is the coins. Something from S2. Pushback. Is this steps of sort all sums? Score sums. The answer is maximized by first saying that okay, we can push all of these sums and sort them. So this is, wait, how can you say that? Isn't that incorrect? So this thing is what I've wrote prior. So I just take the distance either from this or either from this. So yeah, this is correct. So this is the minimum thing you can do. This is enough for the first batch. But also the answer can be maximized with this thing here. And I don't think anywhere else can be maximized the answer. So the answer can be maximized with this is some kind of a sliding window. But this sliding window says that, okay, this can be also like you can take from this set and from this set and the paths inside. So in case the paths do reach more, you take, in case you have more k to work with, then you take all of the paths inside from x to y, but also you have something from S1 and something from S2. But S1, as I understand, S1 is what is outside the thing, what is outside the path, and S2 is what is inside the path, but what is repeated twice. So he divides the problem into three cases. the first one is inside the path. Inside the path from, so inside the path, but this is batch 0. This is the first, like, then there's inside the path after taking, so this is like intersection. This the second thing is intersection inside the path, but what is intersected twice? What is counted twice? And then the third thing is outside the path. And this is if given x and y. So there's only one path here, but there are things that don't lie specifically on the path. And these things are quite different. These don't lie on the path, so the path is this. So he breaks it down like this, and I can see that the so this is S2, this is inside the path but counted twice. S1 is outside. But the thing is that this is what he does, like, convolutionally here with, like, you have two arrays and then you sum up these and then you go and then you push this difference and then you push this difference. So the difference is here from these two arrays, odd and even, are so odd and even. What is odd and even? That's the thing. That's the convex and the concave stuff, which I don't understand, quite frankly. I have seen this somewhere else. Like, this is something that is probably known, how to do this convex dp. There was convex dp, not convex whole dp. No, this is something else. This is let me show you. Convex dp. There was some optimization where you some Japanese author wrote on that. I saw it somewhere. Convex concave, convexity and concavity. Let me see. I know that there was some. Yeah, so like something like this, because there's like can be yeah, something like this. It's concave and convex. Like this is we need to read that maybe sometime other. But I know that I have seen this trick, especially I think on NetCoder. A concave value function extension. I know that there's some trick here involved, but that's impressive. That's impressive if you want to solve. I mean, this. I mean, what I like about this problem, the first problem, is that you have so many different things that you kind of have to realize in order to solve it. First, like, you have to realize the convexity, this this thing of the dynamic programming, then you have to combine it, and then you have to, first of all, you have to realize it's not a DP problem, but rather, I mean, it's kind of DP problem, but it's not the straightforward DP one. But then you have to realize that there's different subsets of vertices that behave differently, and the optimality in all of these subsets. So like the first is on the path versus not on the path from X to Y. And this is quite, so this is the good times R plus, this is quite an interesting, the sum is the sum X is 2 minus. Yeah, I mean, this is some kind of convolutions. If you see that you're reversing stuff here, this is a convolution. But come on, this cannot be this cannot be the official solution. I'm pretty sure. I don't know if this is the official solution. I'm just baffled because this isn't like convolutions are not in the IOI syllabus, right? Like, I mean, maybe knowing the they don't even say it. Wait, what is the what? How is it called? Closing time. Closing time. Not lyrics. What the fuck? What is this song? Closing time IOI 2023 official solution. I want to see like there has to be like what is this closing time? Okay, this is the thing. Solutions to all problems. I will just look at the closing time solution because it's just quite interesting. Models, there's only model solutions. Oh, there are no editorials? Wait, this is quite impossible. There's no editorials. Okay, he solves it with the fanfic tree. Getting high sum of models. DFS distance. Okay, so we have some distance. What do you remember? Distance is the current distance. Parent is the previous thing. Calculate. Yeah, model solution. I found the model solution. I'm just looking at it. But the calculate with. But this is totally different approach. Sorted differences. Sorted values. Sorted differences is Q value and P value. What are Q value? Where they set up these values? Wait. This function is this. Wait. Let's start from the max core function. So okay, this we know that. In path, this is fine. Okay, P value and Q value. Okay, so P value is the minimum and Q value is the maximum. So this is what I said, the invariant, either you choose the P value or the Q value. Then you return then the maximum and calculate with common and calculate without common. So I understand that this without common is without like an intersection, and this should be quite an easy thing, what we already wrote. Without common, but with common is like, okay, so we have some kind of intersection over them, and this is the thing. So the Q value and this is the difference, and then this is the P value, and then this is, so they sort first by by this, the smallest difference, then by this. And now to prove this, that this is optimal is something else. But let's say this sorted values. Now sorted values are 2 times the p-value minus 2 times node minus 2. So he sorts it somehow by nodes, and then there are a couple of more functions. Yeah, but this is convexity. This here is again convexity. Then we go from in path xy. Initially, everything is in P. Get optimal lifetime. Okay. I mean, yeah, but it's based on this principle. I did not expect something like so you can't divide this into many subtasks. Like you can divide every subtask would need a totally different approach. You can't just build on top of some other approach. If you're doing DP, then you cannot possibly build from the DPs to something like this. You have to have an imagination that you can just go to this at the end. You cannot just build and build and build. But okay, so yeah, so this is quite cool. The invariant, the min and max values, and then he tries to plot it out somehow. Wait, there is a similar problem which I solved once, but with quite more complex data structures that needed P. But if you want to take a look at some similar problems, it's like nested dolls problem. Um, this is the if you want to take a look at this problem, this is on Katis nested dolls. This problem, it's quite this. I mean, this convexity. What he's referring is something that I think this in this problem, you have kind of a visualization what is going on. But I'll just post in the chat just for the thing. But yeah, that's incredible. That's incredible. This solution, this knowledge of having all of these things here, I don't know. I won't. I don't even know what to say. I will want to look more deeply. I will look up more deeply in this convexity and maybe make a video on some similar problems. But when you see such a problem, you just always kind of think of greedy solution to some point, and then cleverly just picking out some things. I don't know. But Barbara, what was your solution? If you're still here, what was your solution for the first problem that passed the first couple of subtasks? The first couple of days. I think you had a solution for. You just worked out for the linear problem, right? You probably divided it again on something between x and y and something outside, or for x and y I had an interval which told me you would take these. Yeah, so for x and y, yeah, for x and y, the inside the, but not necessarily you will take inside the interval, right? Lx or x should what? Yeah. So you mean you brute force through through the intervals of which one you will take, but this is what um what's this complexity? It's to the fourth, right? I mean, you could probably make it cubic. It didn't pass the last linear, so this didn't pass. The 14 points one. This passed. Okay. Yeah, I know. Yeah, but it's quite a good solution what you had. For that you needed to take like one with the minimum maximum. Yeah, I mean, I understand what you had. I understand what you had. You had this as far as I understand, it's like x and y, and then this is okay linear, right? And then you had some interval where x took, and then some interval where y took these things. Then, but how did you brute force the intervals? The problem was that I fixed my bug at the end. How do you? Yeah. Yeah. How do you brute force these intervals? Do you brute force through all of these LR, or you just or you actually just brute force through how many how much would you spend on X? You would calculate for every node the distance from X to add Y to it. Yes, of course. That's I mean Y prefix on. Why not just DFS? So you're just looking at as a total like sequence here. And you would have to work out the cases where there is an overlapping and where there is. Yeah, that's the with you wrote a segment as a segment before. Yeah, okay, I understand. Yeah, the overlapping thing is the maximum. Yeah, the overlapping thing is the maximum because you just have to just take the maximum, and this kind of nails it down perfectly. Yeah, okay. I mean, come on. But you succeeded in solving so a couple of subtasks, and that's good. If the road network is linear, that's good. But you see, it's quite an interesting thing that there's nothing much like it's not much different that the road network is linear or it is a tree. The official solution doesn't account for the task that this is a tree. Okay, you have like a DFS, but other than that, everything everything is just as normal. If you check my points on it, you will see that I got it at the end. Oh, you didn't have time to submit it with prefections? Oh, that's bad. That's stupid. Yeah, that's bad. But where was the rankings? Let me see. Let me see what points you have. Let me see. Well, we're talking about this, right? So this is at the end, yeah. So this is at the end. You submit here with 12 points on the third task, and yeah. But quite good for the first day. I mean, it's totally fine. I don't know. Maybe I don't know. The second task I don't like. The third task, even less. It's just, it's typical. It's typical IOI tasks. I'm happy with my performance because I still have chances. I'm not upset. Yeah, for the first time in IOI. Yeah, yeah. For the first time in IOI, that's really good. That's really good. I'm just curious. It has with some at most. No, yeah, I will try maybe to figure out exactly like this concave and convex solution, but not. I don't like. I mean, the understanding needed to solve it like with these convolutions is quite, I think, bigger. You need quite more theoretical knowledge to solve it this way than to solve it in the official IOI manner with like I mean it's still convexity, but they use Panvic tree data structures to simplify things. Maybe there is an even like simpler thing that you can do in order to pass, but still, yeah, I will take a look at this more in more detail. But I'm happy that we take a look that we took a look into everything for the first day at least. No, it's been 3.5 hours. It's exhausting. Like imagine now like 5 hours competing there, and I don't know. I don't at the at now we're discussing and we're like having fun, but when I'm like on ACM, 5 hours is just it's so exhausting and takes takes a toll, and especially these complicated tasks. But so yeah, so you solve these two. We might be able to solve the whole thing with like with this family tree thing all the time. But I won't stream anymore. It's just too late right now. And but I will take maybe I will make another lesson just for the second day because I want to look at the problems as well. And maybe sometime just take a look at this DP convexity thing. It could, but might be very useful. Very useful in some Olympiads. Also I have also there are a lot of problems I want to solve, which I want to upsolve, and more of an ACM style. These are really Olympiad style problems, but I have some ACM problems that I want to solve, which require these more complex theory and algorithms. Uh, but are not as difficult as this, just finding 300 different observations, and they're more straightforward in the way of course, you just get there. But yeah, okay, so okay, in recap, the first problem, just greedily solve it, but like divide these cases. The second problem, I have no apparent clue in how you can solve it under 400 queries. We can optimize, maybe we can do like some random things, and randomizing could work. But 400 queries, I think something to do with like masks and some like binary things here, like fixing some things, and then you decide like make like a segment tree or something. But and this here is some, again, convexity here, some convexity with some sliding window, and you add these things, you add these. When you arrive to a new thing, you need to add them and see how this changes some things later, some things prior, and maybe just go over all of this. But still, this is quite a thing. What else what else are there provided? Failed, incorrect time limit, and time. So these are some solutions that are provided. Common knapsack and other things. Time limit. Greedily wrong answers. So they provide a lot of solutions here. Always have common. Always take. When you check out the problems from the second day, I think you will agree that the second problem is the best out of that day. Yeah, we'll see. We'll see. But as far as I can say, yeah, the first problem is from the first day is the most interesting, I would say, in the way that it teaches you many things. Maybe even the second problem is good, but I don't quite understand it. But the third problem is definitely not something I want to deal with. Definitely not something I want to deal with. So I will just uh, end up the stream right here, since it's been like 3.5 hours. But I would want to more frequently make some streams and just learn about new techniques, new tricks, and maybe talk, just like hang out. So yeah, so I will end it up here, and I see you in the next set caller, call forces streams or whatever. Thank you guys for tuning in, and yeah.